Okay, ladies and gentlemen, thanks for coming today. As you know from the email, the video lecture part 1 today is just a bunch of me talking, and there's no audio, so I'm going to be repeating that question with a little bit more depth here today, and then I'll be posting that for everybody else, but you should be able to answer the first lecture question for here, and then I'll extend the deadline for the quiz to be tomorrow at midnight instead of today at midnight, just to rectify this. So sorry about that. Didn't recognize that had happened, and I don't know why it happened, because I clicked pause and then start the second video, and second video has some audio. So I have some setup issues that I have to figure out for my setup at home. Something's happened. But today we're talking about transient problems. Now I want to make sure you understand transient problems are not on the test, which is on Monday. Okay, so. For those of you, the Monday exam, just let us refresh our memory how it will run. I will be setting out a seating arrangement, because there's going to be slightly different seating arrangement because we have less people that are doing it remotely. But that will be released on Saturday, so you'll know where you need to go, Carter 101, this room, or Fiedler Library to take the exam. If you want to take it remotely, probably for those of you at home, if you need to take it remotely because of a COVID-related reason and you haven't emailed me already, please do so. If you are in statics and you want to take it remotely, please email me. I need you to do it again, because the list has changed so rapidly, so dramatically since the first exam. That being said, exam Monday, get there at 7:15, 7:20, I start reading it. This material is not on the exam. Homework for Wednesday this week is due Wednesday of next week. Today's homework is due Friday of next week. So you have 2 problems on this transient material, one due next Wednesday, one due on Friday. And it's a little bit different material. It provides a little bit different skill set that we have to deal with. So we'll do this problem here and understand what we need to know about this. So first, we're going to have a tank, and I'm drawing just a square tank, but it could be a round tank. When I think of these problems, I think of propane bottles, because I often get to get my propane bottle filled, and it's a transient problem because the mass of my propane bottle after using it is low, and I want to put more mass, more propane inside of that. But this problem is dealing with water, so we're going to be dealing with water, and we have an insulated tank that has a volume of 0.4 meters cubed. Okay, so we put the insulation on here. And it's important to click your tongue when you're doing this. It may annoy the people around you during the test, but it's really worth like 3 or 4 points. So please do so. Insulated tank and volume of 0.4 meters cubed. It contains at state 1, or at its initial time, state 1, it contains saturated water vapor. And we know the pressure is equal to 3.5 bars. And what we want to do is this tank, we want it to end up with, at state 2, we want it to have a pressure of equal to 10 bars. Okay, so we want to pressurize this tank with water vapor. And we do that by in a transient situation. We are going to put into our system just water vapor that is 15 bars and at a temperature of 320 degrees Celsius. So that's what we're doing to fill up this tank. We're putting in pressure 15 bars, 320 degrees Celsius into that tank until we get to our tank is at 10 bars. Okay, so maybe we have some sort of pressure gauge on it of some sort. And my question is, how much mass is added? Okay, now this is like I said, I talked about propane tank. We fill our cars' tires up with air. This is a very common problem that we're going to be dealing with. Putting air into or putting something into a system, taking something out of a system. And that's transient because the mass is changing with time. And because the mass is changing with time, the energy changes with time inside that system. So that is a definition of being transient. Okay, so there are some uniform steps that we need to take to work with transient problems. And the first thing is the same we do with every problem, and we're going to make our assumptions or our model. And so this problem, because it's insulated, we're going to say that our heat transfer is equal to 0. We also know that it's a rigid tank. There are no paddle wheels, no mechanical work. There's no electrical work there, so we can say the work is equal to 0. Nothing in the problem statement indicated anything about a velocity or height change, so we're going to say the kinetic energy and the potential energy, they're approximately equal to 0. What else can we say here? Well, we can probably say that the mass flow rate that's coming into our system, we can say that's constant. We're saying it's a constant mass flow rate coming in. Now, realistically, in a real situation, that mass flow rate may change, but if we're looking at this time period that we're entering up, let's just say that the mass coming in is going to be constant. We're not having some change, because we weren't told anything about how that mass flow rate changes with time anyway, so we'll make that assumption, a simplifying assumption. And if it's a little bit wrong, it's not going to put our answer off by that much. Make all our assumptions. That's step 1. Step 2 is now we start taking the equations and we're going to start simplifying them and integrating them. So the first equation that we're going to deal with is the continuity equation. The change in mass of my control volume with respect to time is equal to the summation of my mass flow rate in minus the summation of my mass flow rate exiting. Okay, I can simplify this because I know there is no mass flow rate exiting. It is our transient systems that we're going to be dealing with primarily are going to be an inlet with no exit or an outlet with no inlet. And we want to figure out how this mass is changing with time, and so that's going to be when we're going to integrate. So we're going to integrate this from 0 to some time t dt, from 0 to some time t dt. Okay, so that's going to simplify our problem a little bit because our first problem, the dt's cancel, and we have the integral of dm, which is just going to be the mass of the control volume at time t minus the mass of the control volume at time 0. Now, this term, we said that the mass flow rate was constant, so this mass flow rate can come outside of the integration because it's constants. All constants can move outside of the integral. And we just have the integral of dt, which when we run this integral, the integral of dt is just going to be t, so it's going to be t minus 0. So basically this integral, we're doing it all in our head here because I think we can, is going to give us m dot times t. Well, if we have a rate times a time, we're going to get an amount. 5 kilograms per second times 5 seconds means we're going to get 25 kilograms of mass. Okay? So what this is just going to be is just mn, no dot. Mn, mass n. And I don't like to write it this way. I like to write it more like this. Mass of state 2 minus mass of state 1 is equal to mass n. Okay? Because sometimes students get confused. Is this times t? No, I'm saying it's a function of t. That's what I'm trying to say here, a function. And so this is time 0 time t. But I like it this way better, and so I'm going to box it because now what I've done is I've taken the continuity equation, I've taken away all my assumptions with it, and I've simplified it to its most basic form for this problem. And I'm done. Always, always, always is how I start my problems. Now, the second problem is going to be, I'm going to do the energy equation. So I'm going to write the energy equation like this. The change in internal energy plus kinetic energy plus potential energy all over the change in time. Now, normally we do dE dt, but that's shorthand because the energy of our system is the internal energy and the kinetic energy and the potential energy. So now I'm expanding it into the 3 forms so I can see it there. Same thing, just different way of presenting it. Is equal to Q dot minus W dot plus the summation of my mass flow rates n times my enthalpy n, my kinetic energy n, and my potential energy n, minus the summation of my mass flow rate exiting times my enthalpy exiting, kinetic energy exiting, and potential energy exiting. I'm doing this in full. You may think, well, I can skip some steps as I write this down, and I totally understand that, but I'm going to do it in full here for this class period. So now we have our first law equation, and we're going to go through with our assumptions. We know that the kinetic energy and potential energy effects are negligible. We know that there's no heat transfer, so that can go away. We know that there's no work or power, so that can go away. And we know there's nothing exiting, everything's coming in as entering, so that whole term can go away. And so we've gotten rid of a lot of things, and now we integrate this from 0 to t dt, and from 0 to t dt. And this is going to give us the internal energy of my control volume at time t minus the internal energy of my control volume at time 0 is equal to, well, the mass is going to come out, because mass flow rate is going to come out of this integral because it's constant. And the enthalpy is also going to be constant, because up here I said that the enthalpy coming in is going to be at 15 bars and 320 degrees Celsius. If that's what's coming in, that enthalpy is coming in as a constant value. I don't have to worry about it changing. And so that can come out, and I'm just going to get that the mass in times enthalpy in is what we're going to have. It's going to take away the rate and just give me this value. Now, again, I don't like to write it in this form. I like to say the internal energy at state 2 minus the internal energy at state 1 is equal to mass in times enthalpy in. And we also say that we don't deal with internal energy, we deal with specific internal energy. So I'm going to write this again as mass at state 2 times internal energy at state 2, specific internal energy at state 2, minus the mass at state 1 times the specific internal energy at state 1 is equal to mass in times enthalpy in. And remember before, we just took mass times U2 minus U1, and that was we were able to do that because the mass was the same in state 2 and state 1. Now, since the mass is changing, we have to split it up. And now I have my second equation. So when I start these problems, the only thing I'm going to do, I'm always going to take the continuity equation and the energy equation and simplify them and integrate them and get them into our final form. And I could do energy equation first and mass continuity second. It doesn't really matter. I just need to get these two forms of the equation. Now, people ask me all the time, Dr. Wakeland, can I just memorize this because I know the integration always happens a certain way. I should just memorize it and I can cancel some things off. And I don't have a problem with you doing that. I just don't think, my personal view on memorizing things is that my memory for short term is pretty good. My memory long term can be problematic. And so if I want to come back to this in a year and I want to figure out how to do it, I can remember I can remember the ideas, the concepts of integration, and I can take my first law equation and I can integrate it and get it back to a point. I think I'm more likely to be able to do the integration than the memorization a year from now. So that's what I tend to go to. I want to look on long-term retention of things, but I don't care which way you do it. I just want to make sure we get the right equation. So once I get the mass continuity simplified and integrated, and I get the energy equation simplified and integrated, simplified, that's what we can call it. We're going to then combine these two things together. These two things are going to come together. We're going to try to put them into one general equation. And what I see here is I see mass in and I see mass in, and so that's what the key is going to connect those two together. I'm going to say mass 2 times internal energy 2 minus mass 1 times internal energy 1, specific internal energy for both those cases, is equal to mass 2 minus mass 1 times enthalpy in. This is an acceptable form. This is now our new general equation that we're going to use to solve our problem. I want to put it slightly different. I want to put the masses, because there's a lot of mass here, I want to put mass 2, internal energy 2 minus enthalpy in is equal to mass 1 times internal energy 1 minus enthalpy in. That's the way I want to put it. It's slightly different. It'll pay some dividends here in the next step, but it's not that big of a deal that we had it in the previous form. Okay, now remember what I'm trying to find. I'm trying to find out how much mass comes into the system. So I need to figure out mass at state 2, I need to figure out mass at state 1. That's what I need to figure that out. And to figure out mass, I know that mass is going to be equal to volume over the specific volume. Okay, so I know the volume, that's set. It's a rigid tank. I need to know the specific volume at these states to help us figure out those values. And maybe solving this problem is going to help me find some specific volumes. So what I'm going to do here is I'm going to recopy the state information that I had earlier for state 1, state N, and state 2, so I don't have to keep scrolling up into the on my screen. And I know that state 1 is a saturated vapor. I know the pressure at 1 is equal to 3.5 bars. I know the specific volume of 1 is equal to, well, let me just do that. I had the time today. Let's go and look at that. Saturated vapor, 3.5 bars. So I'm looking at water. And so I'm going to go to my tables, and I'm going to go to my water tables at 3.5 bars, table A3. Table A3. And 3.5 bars is right here. I'm looking at saturated vapor, so here's my value. Saturated vapor, 0.5243, 2546.9, and 2732.4. Those are my values for saturated vapor at 3.5. So that's what I want to write down on my page so that I can do my calculation. So 0.5242 meters cubed per kilogram. My internal energy 1 is equal to 2546.9 kilojoules per kilogram. And my enthalpy at 1 is equal to 2732.4 kilojoules per kilogram. This should be a pretty easy property lookup. If you had some issues with that, we need to talk, because next Monday night is not going to be kind to you if that was a difficult property lookup. Maybe a little bit more challenging property lookup, but something I still think that you should be able to do quite easily. If we had 15 bars and our temperature was equal to 320 degrees Celsius, I need to figure out what the state is here. And I want to find out what my specific volume is, and my internal energy is, and my enthalpy is for all those things, just to keep consistent here. So the way I'm going to do it is I'm going to go to my tables, and the first thing I always do is check if I'm going to be saturated or not. Okay, so I go to 15 bars. 15 bars, I know the saturation temperature is 198.3. Well, we're at 320. We're above that, so I know I'm a vapor. Okay, now I'm confirmed that I can go to the vapor tables. Maybe you knew that already. I want to check. In the vapor tables, I can go to my second page of my vapor tables where I have a nice thing, superheated water vapor, 15 bars, and I can look and I can say, well, 320 degrees Celsius. Here we are, 320 degrees Celsius, and I can read off what my specific volume is, what my internal energy is, and what my enthalpy is. And those are going to be my three values that I'm going to find and write down onto my page here in a moment. So those values are 0.1765 meters cubed per kilogram, 2,817.1 kilojoules per kilogram, and 3,081.9 kilojoules per kilogram. All I know about state 2 is that I'm at 10 bars. And that's a problem here because I can't set the state of water with just knowing the pressure. I need to know two things. I can't even do a liquid approximation. I mean, if it would be a liquid, I don't think it's a liquid, but even then I need my temperature. Okay, so I'm in a little bit of a problem here that I can't set my state 2. Okay, so let's see where that's going to lead me here. I'm going to rewrite the equation down here. Mass 2 times U2 minus Hn is equal to mass 1 times U1 minus Hn. Okay, I'm going to highlight what I know. I know my state 1, and I know my enthalpy N. I can calculate my mass. Okay, so let me rewrite this here. I can say volume over specific volume 2 times U2 minus Hn is equal to volume over specific volume 1 times U1 minus Hn. And again, I know these things, this one, and this one. I also know my volume, and I know my specific volume at 1. So I'm missing the information from state 2, U2 and V2. And usually when I get to a situation like this and I'm missing something, that means I need to find another equation to help me figure this out. But I've used my equation for mass continuity, and this is not an ideal gas, so I can't use the ideal gas equation. So I'm kind of stuck here. And we often get to this very place on these problems. And why I'm showing this to you is because we get to this place a lot on these type of problems. And what our best way to approach this is to guess. And we don't guess just randomly. We do something called iteration or guess and test. Okay, we know that the pressure at state 2 is going to be equal to 10 bars. We're going to guess a temperature at state 2. And once we guess that temperature, we're going to be able to set the state, and we're going to find a specific volume 2 and an internal energy 2 and plug it into the equation and see if that satisfies the equation. And if it does, we're done. And if it doesn't, we're going to guess again until we can get to a place where we can find the correct answer. All right? Now, your homework problem that I gave to you on Wednesday isn't guess and test. Your homework problem I gave to you today is not guess and test. And I would never give you a guess and test problem on an exam. That's just not unfair. Okay? But I want you to know that this technique is something that you're going to often see with these problems. So we're going to go through it here together. I am going to give you an alternative homework assignment, one of these alt assignments that you can work on, that you can guess and test. And I'm going to do it manually, but what I want to recommend on that alternative assignment is you use Excel to help you do it, because Excel can really do it really quickly, guess and test. You can put the table values in for 10 bars, and it can iterate for you. It can interpolate for you, because there's going to be a fair amount of interpolation here. But before we get there, let's see, how would I guess and test in this problem? Well, I want to see what the final pressure is it 10 bars, what the final temperature is. You know, my first guess might be that the final temperature is the temperature of the steam coming in, which is 320. So I'm going to guess 320 degrees Celsius. Okay, so if I go to my table, 10 bars is right here, and 320 degrees Celsius is actually right on my tables. And so here's my value for specific volume, and here's my value for internal energy. So I would just put those values in here. The values are going to be, and let me make sure I go to the place where I have this, my specific volume is going to be equal to 0.2678 meters cubed per kilogram. My internal energy is going to be equal to 2826.1 kilojoules per kilogram. Okay, so here's what my equation will look like. 0.4 meters cubed divided by 0.2678 meters cubed per kilogram times U2, which is 2826.1 kilojoules per kilogram, minus my enthalpy in, which is 3081.9 kilojoules per kilogram. And that's going to equal 0.4 meters cubed divided by the specific volume of 1, which is 0.5242 meters cubed per kilogram, times U1, which is 2546.9, and Hn, which is 3081.9 kilojoules per kilogram. Now the good news is we're just changing these values here. Which values? We're changing this value here, and we're changing this value here in this equation. So this side, the right-hand side, is always locked in. This is always locked in, and the answer for that right-hand side is going to be always equal to negative 407.6 kilojoules. We just want to see if the left-hand side is equal to negative 407.6 kilojoules. So if we do this calculation, and I'm not going to plug it into my calculator, I have it already here. If we do the left-hand side of this, we get that the answer is negative 382.08 kilojoules. We're too high. We need to go lower. We need a more negative answer. So we have to think about what to do. And so that means we have to guess again. So again, our pressure 2 is going to be equal to 10 bars. And our temperature 2, we have to guess something. And you know what? It's hard to guess which way we need to go, but let's just, let's look at our document camera here. Let's look at our thing. We have a choice here. I'm going to try to guess one of these two values. I'm going to guess 360 or 280. And you know what? I'm going to go with 280 first as my answer here. And so I'm going to say that this is going to be equal to 280. And I'm going to put these values in for my specific volume. So my specific volume at 2 now is going to be equal to 0.2480 meters cubed per kilogram. And U2 is going to be equal to 2760.2 kilojoules per kilogram. And so I'm going to put that in the equation. All right, so we're going to get 0.4 meters cubed divided by 0.2480 meters cubed per kilogram is equal to 2760.2 minus 3081.9 kilojoules per kilogram. And we want all that to equal negative 407.6. Well, what we're going to find when we calculate this, when I guess 280, is negative 518.87 kilojoules, which is good. We've now bracketed the answer. We have first, our 320 was too high. Our 280 was too low. And we know we were closer at 320 than we were at 280. And so we would keep guessing and guessing and guessing and guessing. Okay? Now, the problem with this is now all of our guesses involve us interpolating. We have to interpolate, because if we look back here to our table, we don't have any entries between here. So our next guess is probably going to be 300, which is halfway between, because it's a nice, easy thing to do. And so I'm not going to have us do that. I'm just going to show you the work here. So I'm right here. It must be between 320 and 280, so my guess is 300. So that gives me, when I interpolate, this is my specific volume, this is my internal energy. And so when I do that calculation, my answer is negative 447.85. So now I know that my answer must be between 300 and 320. Okay, so that's what I know. I know my answer is between 300 and 320. Okay, so I say, all right, I'm going to guess 310. That's my specific volume, that's my internal energy. Now I do this again, my answer is negative 414.26. Okay, now I know my number must be between 310 and 320. So I go up again and guess 315. And here's my specific volume, and here's my internal energy. And now I've found that this number is negative 398.01. And that actually means that, 320 is not my lower bounds. Now 315 is my lower bounds. And now I'm between 310 and 315. Okay, and I'm going to keep doing that. Really, when it comes down to the final bit of it, when we get down here, we are interpolating between these two numbers. We are assuming that between 280 and 320 that we have a straight line between these two things. So really, once we find the two corresponding places in the chart where we can connect, that we assume there's a line, a linear interpolation to that we can interpolate to find the answer. I actually went a little bit further than what I needed to do. But because I'm interpolating to get these values, what I can do is just interpolate to get my final temperature. Okay, so what I did was, and I'll move over here to my tablet and keep going here. I know that 310 gave me a value, and 315 gave me a value. So what did my 315 gave me a value of negative 398.01, and my 310 gave me a value of negative 414.26. And remember, we didn't know what T2 was, but we know that T2 gave us a value of negative 407.6 kilojoules. So our interpolation is going to be the following. We're going to say 310 minus 315 all over negative 414.26 minus 398.01 is equal to T2 minus 315 all over negative 407.6 minus A minus 398.01. And we're able to find out what our T2 is that way. And that temperature, when we do that, is going to be about 312 degrees Celsius. So do we understand this iteration? Okay, it's a valuable technique. I don't think with the tools that you have available to you that manual iteration is a good use of your time. I would make a small Excel spreadsheet that would do that all for you fast. Okay, that's what I would do, and that's what I'm going to ask you to do on your alternate homework. So actually the quiz question for today is this question. Question for part A is the following. It says, what is the technique that Dr. Wenkland used to solve this problem? Is it iteration, interrogation, interpolation, or intoxication? I think you know that the answer is going to be A, iteration. That's what we have here. So those of you at home that are just now watching this, you probably now are going to click A and then stop watching this video. Have a good weekend. But let's finish this, please, so that we can finish and understand what we need to do here. Now that we know the temperature, we still have to find out what mass is at 2. So now we know that our pressure is going to be equal to 10 bars, and our temperature 2 is equal to 312 degrees Celsius. So we have to interpolate to find out what the specific volume is at 2. Okay, because that's not on our tables. 312 is not on our tables, but we can interpolate, and that would give us 0.26384 meters cubed per kilogram. And again, I'm going to put this as by interpolation. Okay, and now that we know that, the mass 2 is going to be equal to the volume over the specific volume 2, which the volume is 0.4 meters cubed divided by 0.26384 meters cubed per kilogram. And this is going to give me 1.52 kilograms. So mass 2, good thing, it's bigger than mass 1. That's what we need. I guess I didn't calculate mass 1. Mass 1 is equal to volume over specific volume 1, which is 0.4 divided by, where did I have it here? 0.5243 meters cubed per kilogram, which is equal to 0.762 kilograms. So our equation basically said if I subtract mass 2 from mass 1, I get how much mass is added to the system. I mean, that's obvious. I mean, I could give that to a student that goes to KU, and they could probably understand that. You understand how that works through the equation of continuity, but it's a simple idea. If I take the mass at state 2, subtract from the mass at state 1, I know how much mass is added to it. And when we do that, we get 0.754 kilograms. It's a very easy calculation, but getting the property that we needed for that was very challenging. Okay, so that's the skill that we need to know. And that's unfortunately, or fortunately, that's how a lot of these problems are needed. Many times I'm creating and this is not on this is not on exam 2, but on exam 3, from time to time I put a transient problem on the exam, and when that happens, I have to make sure that I don't do a problem that needs you to guess and check. Okay, so that requires me to pick the right values. But as an engineer, this is a valuable technique, because we can set that, and there's going to be property lookups, computer programs that you can use that will help you even more than what we're doing right there. Are there any questions about this problem? The main thing you need to know is those first steps: simplifying the two equations, combining together, getting the working equation. Okay, in the last 10 minutes or so that I have, I don't have enough time to really go over the two problems I want to, but I want to show you a problem that I would present, and I also want to talk to you about a problem. So one of the things I was going to do today is say, you know what, we've said a very important thing. We've said that when the enthalpy is entering or leaving our control volume in these transient problems, we're going to assume for this class that enthalpy is constant. And that is true for most for our problems. But in reality, a lot of times when the gas is entering or leaving a system, the enthalpy is going to change. And you have the ability to solve a problem where the enthalpy is changing, but that is just another level. I want to scaffold this class and to get you, okay, I know this stuff. When the enthalpy changes, that puts us into another level here. We're going to have to figure out how to get up there. And I think you all could, but not in the time I want you to. That's more of a graduate level thing that you'll eventually work with. I was going to show you how that problem works and the complications that simple assumption, removing that simple assumption makes can cause our life to be much more challenging. So that was one of my example problems. Just know it's tougher. It's tougher and it is it's not straightforward. Okay, but it's within your ability. I am going to show you though just a exam problem from the fall of 2012. Sorry, that I think is good. And so this is very similar to what we did here today, but now we have water vapor is leaving this, actually saturated liquid leaving. So I had a rigid tank, 0.3 meters cubed, is filled with saturated liquid water at 200 degrees Celsius. And we have a valve here at the bottom of the tank that allows liquid to be withdrawn from the tank. Heat is transferred to the water so that the temperature of the tank remains constant. And that's important. The temperature of the tank needs to remain constant because we want the enthalpy of the water leaving it to be the same. And if the temperature is changing, the enthalpy changes. So we want to have heat transfer in to keep the temperature constant. And so this is very similar to the second example I did on the video lecture today. Just because it says constant temperature does not mean there's no heat transfer. Here, to keep that temperature constant, what the temperature was going to want to naturally do is go down. But we're adding heat from the environment into this to keep the temperature constant. So if I put my hand on the side of this tank, what would I feel? It would feel cold because heat would be leaving my hand into the system. Okay. Heat is transferred to the water such that the temperature of the tank remains constant. Determine the amount of heat in kilojoules that must be transferred by the time 1/2 of the total mass has been withdrawn. Okay? So we're going to do the same things here, and I actually did these in reverse order. I took the energy equation and simplified it. Now we have heat and we have mass exiting. I took the mass equation, I simplified it. And then I took these two equations and I put them together. Now there is a little thing here. I put minus mass exiting. I have minus mass exiting, so when I replaced in the minus mass exiting, it's going to be plus M2 minus M1. Okay? I found my general equation. I solved for my Q. And then I knew that mass 2 is equal to 0.5 of mass 1, so I replaced every place where I had mass 2, I replaced it with mass 1, and then I wrote it into this form. Okay? This is my governing equation. That's most of the work I had to do there was this. Now my thing is I have to find the properties. Okay? We find the mass at 1 just the same way we found the mass at 1 in the last thing. I take the volume and I divided it by the specific volume. Okay? I can set my state. Up here it's at 200 degrees Celsius, saturated liquid. I can set my state there. Okay? I can also find if I know my initial mass, I know half of that is the final mass, so I can find that value. I know my internal energy because if I set my state here, it's a saturated liquid at 200, I can find my internal energy, and it's leaving this as a saturated liquid at 200 degrees Celsius, I can find my enthalpy exiting. Okay, the hard part is defining the state 2 because state 2 changes. But I do know that the volume of the state 2, and I do know the mass of state 2, volume of state 2 is the same, mass of state 2 is half. I can divide these two values and I can get the specific volume of state 2. And once I get the specific volume of state 2 now, I can set the state. Okay, because it's going to be at 200 degrees Celsius and it's going to be at this new specific volume. Well, when I do that, it tells me that it's a saturated liquid, saturated mixture, sorry, and I can find the quality, and the quality is very, very low. It's almost a saturated liquid. If we assumed it was a saturated liquid, we'd be pretty darn close, but it's actually a little bit off. It's almost 1% by mass vapor. And so I find the quality, and I use that quality to find out what the internal energy is. Okay, and now that I know the internal energy, now it's plug and chug. All right, this step here, finding out what the state is at 2, is the tough part here. This is where the understanding and storytelling of the problem really comes in. This is just algebra and math. There's some thermo up here. Here's where that, how do we set that state, really comes into play. And that's where that thought process comes. So as we go look at these problems, you need to understand both of these two types of problems. You need to understand a tank that has an exit but no entrance, and a tank that has an entrance but no exit. If you can solve these two types of problems, I will not, I'm going to give you one of those two if I choose to put this problem on the test, transient problem on the test. One of those two problems are going to be given to you. That's what we're going to be working with. Now, in reality, you could have problems where the fluid coming into the system is more than the fluid going out, and that's transient, or it's going out more than it's coming in, and that's transient. But that we're going to only work with these type of things in our initial investigation here in Thermo 1. Okay, that's what I have for you today. Are there any questions? All right, for the exam on Monday, what I'm going to recommend to you all to do is to come up with depending on how comfortable you are with problems. If you're comfortable with the problems, then go for it. But if you're not, what I'd like for you to do is come up with a flow chart of questions that you ask yourself when you're solving a problem. First question should be, is it open or closed? Does mass cross the boundary or not? That puts you in two different things. Once you know if it's open or closed, if it's open, write down the open system equations. If it's closed, write down the closed system equations. If it's an ideal gas, put the ideal gas equations below that. And then systematically go through each equation and ask yourself, is internal energy, is kinetic energy, is potential energy, is heat transfer? Ask yourself those questions and simplify it, okay, down to its final form. And then go out and start finding some states and find those states. If you get the equations right and simplified down and you can set the states, man, that is so many points on this exam. That's so many points. 75% of the points is probably right there. Now using techniques to solve it, to get it right, then that gets you to the rest, the remaining points. But I am most concerned with your thought process. The final answer be damned. I want your thought process. So work on that thought process. Then look at your equation sheet. Make sure you understand the equation sheet. Make sure you understand the way I presented the equations on your equation sheet. Then, when you're done with that, go to look at the exam problems I posted. And first, put your pencil down and look at the problem statements without looking at the answers and see if you can tell the story of the problem. Can I tell the story? What's it looking for? And then put yourself under a time constraint. 30 minutes per page. Can I answer this problem? Okay, that's how I would study. Monday, there will be no video lecture. No video lecture on Monday. There will only be an in-person session on Monday. It's optional to come to. All I'm going to do here in the in-person session is go over the equation sheet, ask you some, if you have any questions, and we'll go over that. Okay? All right. I have officially got all the way up to 1:14. You can go. Have a good weekend. Let's beat the Horned Frogs.